All right, get ready for a deep dive. We're about to take off into the world of aerodynamics. You've really outdone yourself this. Time diagrams, textbook chapters, even some incredible images.
You make it sound like a top secret mission.
Well, it kind of is, isn't it? We're trying to unlock the secrets of how planes actually stay up in the air,
And you know what? It's not magic.
though it might seem like it sometimes.
Exactly. It all comes down to physics and some pretty incredible engineering.
From what I'm seeing here, we're going to explore the forces that make flight possible, especially lift and drag.
Ah, yes. Lift and drag, the heart of it all.
And get this, we've even got ground effect and wake turbulence on the agenda. Sounds like things could get a little bumpy.
Indeed. Understanding these forces isn't just for pilots. It's about appreciating the sheer genius that goes into designing a machine that can, well, defy gravity.
Okay, so the first thing that jumps out from this stack is a section about the four fundamental forces acting on an aircraft: thrust, drag, lift, and weight. The Fantastic Four of flight, right?
Exactly. And these forces are always at play, constantly interacting.
But I have a feeling it's not quite as simple as they make it sound in those introductory physics classes, right?
You're right. It's not as simple as just saying thrust equals drag, lift equals weight. There's a dynamic interplay going on, with each force influencing the others.
So it's less like a basic equation and more like a four-way tug of war.
You could say that. For instance, even when an aircraft is cruising smoothly in level flight, thrust might have a slight upward angle.
Meaning it's not just counteracting drag in a perfectly horizontal direction.
Exactly. Which means weight isn't the only force countering drag. It's all about understanding how these forces break down into their components.
Okay, I'm starting to see how this gets complex quickly. Now, let's talk about lift, the force that literally gets the plane off the ground. People often talk about wings pushing air down, but I'm guessing there's more to it than that.
You're right, it's a bit more nuanced than that. The pushing air down idea is a simplification. Lift is mainly generated by the difference in air pressure above and below the wing. Faster moving air has lower pressure. That's Bernoulli's principle in action.
And I see that illustrated in one of these images. The airflow is faster over the curved upper surface of the wing, creating lower pressure there compared to the slower airflow underneath.
Precisely. It's like the wing is being pulled upwards by this pressure difference. And the angle at which the wing meets the oncoming air, we call that the angle of attack, plays a crucial role.
Hold on, I'm getting flashbacks to my driver's ed teacher telling me to stick my hand out the car window. Is it like the steeper the angle of your hand, the more the air pushes up on it?
That's a great analogy. The steeper the angle of attack, the more lift is generated. But here's the catch. If you go too steep, the airflow detaches from the wing, and you get a stall. It's like the wing suddenly loses its grip on the air.
Right, stalls. We'll definitely have to unpack those later. But before we leave lift, I'm drawn to these mesmerizing images of swirling air patterns trailing behind the aircraft. Wingtip vortices, right? What's the story there?
Ah, those are a visual representation of induced drag, an unavoidable consequence of generating lift. It's like the universe's way of saying, you want lift, here's a little drag to go with it.
So those mini tornadoes behind the plane are actually a byproduct of the lift being created. It's like a hidden cost.
Exactly. And unfortunately, those vortices can be dangerous to other aircraft trailing up behind. That's what you hear about wake turbulence.
Speaking of drag, I see a whole section here dedicated to this aerodynamic adversary. It seems like there are multiple types of drag an aircraft has to overcome.
There are indeed. We've got parasite drag, any drag that's not associated with producing lift. Imagine a sleek aerodynamic jet versus a clunky boxy plane.
Okay, I'm picturing it.
The clunky plane will experience more parasite drag because its shape creates more resistance as it moves through the air.
So, streamlining an aircraft's design, making it as smooth and slippery as possible, is all about reducing parasite drag, like giving it the best possible chance to slip through the air.
Absolutely. Think about how easily a sphere moves through water compared to a flat plate. The shape of an object has a huge impact on how much drag it experiences.
Okay, so we've got our four forces: lift, drag, thrust, and weight. Now, how does an aircraft manage all these forces during maneuvers like turns and climbs? It feels like things would get really complicated really quickly.
And you'd be right, it does. It's all about maintaining a delicate balance. Imagine an airplane climbing.
Okay, I'm picturing it.
The thrust vector, the direction of the engine's force, isn't perfectly horizontal. It has an upward component to help overcome that downward pull of gravity.
And I see an image here depicting the forces during a climb lift is greater than weight. thrust is overpowering drag and up goes the plane. It's fascinating to see these abstract forces visualized.
Visuals definitely help make sense of it all. And in turns, it gets even more dynamic. The aircraft has to bank, and that means the lift vector needs to tilt, creating a horizontal component that pulls the aircraft into the turn.
I vaguely remember those diagrams from my brief and somewhat disastrous flirtation with flight simulators. Different types of turns, different forces at play. It seems like pilots are constantly walking this tightrope of balancing forces to maintain control.
That's a great way to put it. Pilots are masters of manipulating these forces, making subtle adjustments to stay aloft and on course.
Okay, before we move on to those fascinating phenomena we touched on earlier, ground effect, wake turbulence, what stands out to you as the most mind-blowing thing about this whole force interaction?
It's this. Flight isn't about any one force dominating. It's about the constant, intricate interplay of all four forces. This dynamic dance that keeps an aircraft soaring through the sky. It's a testament to both the laws of physics and the brilliance of engineering. It really makes you appreciate the skill of those pilots up there, doesn't it? Wrangling those forces, keeping everything balanced.
Absolutely. It's like a whole other world up there, governed by these invisible forces. And speaking of which, we touched on ground effect and wake turbulence earlier.
Ah, yes. Two phenomena that highlight just how dynamic the world of aerodynamics really is.
Let's unpack those a bit more. Ground effect, that's that floaty feeling pilots talk about during takeoffs and landings, right? What's actually going on there?
So imagine this. As the aircraft gets close to the ground, the Earth acts like a giant mirror.
Okay, I'm trying to picture it.
This mirror reflects the wing's downwash back up at it. This reflected air creates a cushion of air that reduces induced drag and increases lift, making the plane feel like it's surfing on a wave.
So the closer you are to the ground, the more lift you get and the less drag you experience. It seems counterintuitive, but that's what makes it so cool.
Exactly. Pilots actually have to account for ground effect during landings.
Oh, I bet.
If they don't anticipate that extra lift, they might end up floating down the runway longer than intended.
Now, about wake turbulence. I know it's a safety hazard, but can you give us the rundown on why those wingtip vortices are such a big deal? We see the cool pictures and videos, but what's the real danger there?
Well, remember those mini tornadoes we talked about? Trailing behind the aircraft?
Oh, yeah, like invisible whirlpools of air.
Yeah, those swirling masses of air can persist for some time, posing a real hazard for any aircraft falling behind.
So if another plane gets caught in those vortices, it's like hitting an air pocket on steroids.
Essentially, it can cause sudden rolling motions, even a loss of control in extreme cases. That's why pilots are trained to maintain specific separation distances during takeoff and landing.
It's like a carefully choreographed aerial dance, avoiding those invisible whirlpools.
That's a great way to put it. There's a lot more to it than just pointing the plane in the right direction. Pilots are always thinking ahead, anticipating those potential hazards.
And speaking of anticipating hazards, let's switch gears to another fascinating topic.
Yeah.
Aircraft stability. How does a plane manage to stay relatively level and on course without constant pilot input? It's not like they're glued to those joysticks every second.
That's right. And it's a great question. It all comes down to design, how those four fundamental forces we talked about earlier interact to create stability.
So it's like the plane is designed to naturally want to stay balanced in the air.
Exactly. It's about finding that sweet spot where the forces harmonize, creating a stable platform for flight.
Like finding the perfect balance point on a seesaw.
Exactly. And the wings themselves, their design plays a huge role in stability. For example, dihedral, that slight upward angle of the wings.
Oh yeah, I see it in this diagram. It's subtle, but it's there.
Right. That dihedral angle helps create a self-correcting mechanism. When the aircraft starts to roll, the dihedral angle creates more lift on the lower wing, naturally pushing it back towards level flight. It's like the wings are constantly trying to right themselves.
Wow, so even a slight design element like that can have a big impact on stability. Amazing.
It's true. Even small design choices can make a big difference when it comes to aerodynamics. And then there's sweep back angling the wings backward. That can help delay some tricky aerodynamic effects at high speeds, but it can also make the aircraft prone to something called Dutch roll.
Dutch roll. Okay, now we're
Okay.
talking. What is that? Some kind of fancy aerobatic maneuver?
Not quite. Imagine it as an awkward dance move, a combination of rocking and yawing. It's not dangerous, but it can be a bit disconcerting for pilots. Thankfully, modern aircraft are designed to minimize this effect.
That's good to know. I'd rather not experience any awkward dance moves while I'm thousands of feet in the air. But seriously, it's amazing to think about all these subtle design elements working in concert to create a stable and controllable aircraft.
It's a testament to the ingenuity of those aircraft designers, that's for sure. And it's not just about static stability, you see.
Static stability.
Right, how the aircraft behaves when it's just sitting there.
Hmm.
We also have to think about dynamic stability, how it responds over time to disturbances in the air.
Ah, so it's not just about staying balanced, but about returning to that balanced state smoothly.
Exactly. Like a ballet dancer gracefully recovering from a misstep.
Instead of a clumsy oaf like me tripping over my own feet.
Precisely. But even the most brilliantly designed aircraft needs to be loaded correctly. Weight and balance play a crucial role in stability, too.
Right, I see a whole section here emphasizing that pilots need to understand how loading the aircraft affects its center of gravity.
It's crucial. Too much weight in the wrong place could make it unstable, even dangerous. It's not just about the total weight, but how that weight is distributed. If the center of gravity is too far forward, the aircraft might be nose-heavy. Too far back, and it could be tail-heavy. Neither of those is ideal.
And I see an image showing how different loading scenarios can shift the center of gravity, impacting the forces acting on the aircraft, like a delicate balancing act, making sure everything is just right.
And that's why pilots carefully calculate weight and balance before every single flight. It's one of those essential pre-flight checks that helps ensure a safe journey for everyone on board.
It's incredible to think about all these factors coming into play. From the shape of the wings to the distribution of weight, it really highlights the complexity of flight.
It's true, it's a complex system, but you know what? There's one more layer of complexity we haven't even touched on yet.
Oh no, don't tell me. What else could there be?
High-speed flight.
High-speed flight. Now we're getting into the really exciting stuff. Approaching the speed of sound, breaking the sound barrier, it's like stepping into a whole other dimension of aerodynamics.
Exactly. And at those speeds, the rules of the game change dramatically. At those speeds, the air around the aircraft behaves in completely different ways. We move from subsonic flow, where the air is moving slower than the speed of sound, to transonic flow.
Transonic flow, it even sounds fast. What happens then?
Well, in transonic flow, some parts of the aircraft might actually be exceeding the speed of sound.
Whoa, so part of the plane is supersonic, but part of it isn't. What happens then? Does it, like, rip itself apart?
Thankfully not. Aircraft designed for transonic flight are built to handle those stresses. But eventually, if the aircraft is designed for it, we reach supersonic flight, where the entire plane is exceeding the speed of sound. And that's when things get really interesting.
I can only imagine the forces involved must be incredible at those speeds.
They are. And that's why supersonic flight requires such specialized aircraft design. Even something as simple as the shape of the nose cone can have a huge impact on how the aircraft handles at supersonic speeds.
And what about those shock waves we see in images of supersonic aircraft? They look, well, pretty intense.
They are intense. As the aircraft punches through the air at supersonic speeds, it creates these pressure waves that radiate outward. Imagine the wake of a boat.
Okay, I'm picturing it.
It's kind of like that,
Oh.
but far more energetic. These shock waves are what cause the sonic boom we hear on the ground.
It's mind-blowing to think about these invisible walls of pressure being created as the aircraft slices through the air. It's like something out of science fiction.
It really is. And, those shock waves don't just make noise. They also create a tremendous amount of drag, which is why supersonic aircraft need such powerful engines.
So it's not just about going fast, it's about overcoming those incredible forces that come with approaching and exceeding the speed of sound. It's like a whole other level of engineering mastery.
Precisely.
Yeah.
And it requires a whole other level of pilot skill to manage those forces and fly safely at supersonic speeds.
Speaking of limits, we talked about the flight envelope earlier, those boundaries that define an aircraft's safe operating limits. I imagine those limits become even more crucial at supersonic speeds, right?
Absolutely. Exceeding those limits at such high speeds could be catastrophic. The flight envelope for a supersonic aircraft is much narrower than for a subsonic aircraft, and pilots need specialized training to operate within those tight margins.
So it's like walking a tightrope while juggling chainsaws.
That's one way to put it. But seriously, it takes incredible skill and precision. Now, while we're on the topic of limits, there's another crucial concept we need to discuss, one that's closely related to those high speeds. Load factor.
Load factor. That rings a bell. It's about the forces an aircraft experiences during maneuvers, right? Like pulling up from a dive or making a sharp turn.
You got it. Load factor is essentially a measure of stress. It's the ratio of the lift generated by the wings to the aircraft's weight.
Okay, so if lift equals weight, the load factor is 1.
Exactly. In straight and level flight, load factor is usually 1. But when you start throwing in those exciting maneuvers,
Things get a lot more intense.
you could say that. Imagine pulling up sharply from a dive. You're increasing the lift generated by the wings to change direction.
And that means more stress on the aircraft.
Right. The load factor goes up, and the structure of the aircraft is now experiencing forces several times greater than gravity.
Wow, I'm starting to see why load factor is such a big deal. It's like those diagrams we've all seen of roller coasters showing the G-forces at different points on the ride, except in this case, it's not just about the thrill, it's about the structural integrity of the aircraft.
Exactly. Every aircraft has a limit to how much load factor can safely handle. Exceed that limit, and you risk serious damage, even catastrophic failure.
So how do engineers determine those limits? Is it just about building planes super strong, or is there more to it?
It's a combination of things. The design plays a huge role, the materials used, the construction techniques, the shape of the wings and fuselage. But it's also about rigorous testing. Engineers put aircraft through their paces, simulating extreme maneuvers and stresses to make sure they can handle the loads they might encounter in flight.
That's good to know. It's like those crash tests they do with cars, but in this case, they're trying to prevent the crash from ever happening in the first place.
Exactly. And just like different types of cars are designed for different purposes, different categories of aircraft have different load factor limits. A small general aviation aircraft used for leisurely flights will have a lower limit than, say, a fighter jet designed for high G maneuvers.
Makes sense. So how does a pilot keep track of load factor during flight? It's not like they have a G meter on their instrument panel like they do in those fighter pilot movies. Or do they?
While some aircraft do have G meters, pilots primarily rely on their instruments and, more importantly, their training and experience. They develop a feel for how the aircraft responds to control inputs and how different maneuvers affect the load factor.
It's like they develop this sixth sense for how much stress they're putting on the aircraft.
In a way, yes. It's about listening to the aircraft, understanding its limits, and operating safely within those limits. And that brings us to another important concept, one that can be particularly relevant when we're talking about load factor and the limits of what an aircraft can handle: stalls.
Stalls. Now we're getting into the realm of things that make even seasoned flyers a little nervous. It's like the boogeyman of aviation. Everyone knows it's a possibility, but nobody wants to talk about it.
It's understandable why people get nervous about stalls, but the key is to understand what's really happening. A stall occurs when the angle of attack of the wing, remember, that's the angle at which the wing meets the oncoming air, exceeds a critical angle. When this happens, the airflow over the wing separates, and you get a sudden loss of lift.
So it's not just about speed, it's about the angle of the wing. That's a bit of a revelation for me. I always imagined stalls as happening only when the plane was going too slow, like it was running out of steam.
That's a common misconception. While stalls are more likely to occur at lower speeds, they can technically happen at any speed if the angle of attack gets too high.
So you could be cruising along at a perfectly normal speed, but if you pull back too sharply on the controls, increasing that angle of attack, you could potentially stall the aircraft.
That's right. That's why pilot training emphasizes recognizing the signs of an approaching stall and taking corrective action before it happens.
Okay, good to know. So what are the telltale signs? What should a pilot be on the lookout for?
One of the first things a pilot might notice is a buffeting or shaking of the aircraft. That's the airflow starting to separate from the wings. They might also feel a mushiness in the controls, like the aircraft is becoming less responsive.
I imagine ignoring those warning signs would be a very bad idea.
You got it. If the stall continues to develop, the aircraft will start to lose altitude, and you could even enter a spin, which is a much more serious situation.
Okay, so let's say a pilot finds themselves in a stall. What's the recovery procedure? What actions do they take to regain control?
The most important thing is to reduce the angle of attack, essentially. Get the wings back to a point where the airflow reattaches and they can start generating lift again. This usually involves pushing the control yoke forward, lowering the nose of the aircraft.
It seems counterintuitive if you're losing altitude. Your instinct is to pull back on the controls, not push forward.
It does seem counterintuitive, but remember, you have to get those wings back to generating lift. And once the airflow reattaches and the aircraft starts regaining lift, the pilot can then apply power to regain altitude and resume normal flight.
This deep dive has really taken us to new heights. We've covered so much ground, no pun intended, From the fundamental forces of flight to the mind-boggling world of supersonic speeds. And we even touched on those nail-biting moments when those forces aren't quite in harmony, like stalls.
We did. It's been quite a journey through the world of aerodynamics.
It really makes you appreciate the complexity of what's happening every time you step on an airplane. It's not just engines pushing you forward, it's a delicate dance of forces, a testament to human ingenuity and our understanding of the laws of physics.
It is, and next time you're looking out the window at 30,000 feet, I bet you'll see it all in a whole new light.
I know I will. This deep dive has been truly eye-opening. Until next time.